Something rose out of the North Sea on the first day of 1995. That should not have been there. The Draupner oil platform stood in those waters off the coast of Norway, a steel structure anchored to the seafloor, in water deep enough that a 10-story building would disappear entirely beneath the surface. It had been engineered for extremes. Its designers had worked through every scenario the North Sea might plausibly deliver, calculated the forces each scenario would impose, and built a structure rated to survive them. The platform carried a laser gauge mounted above the sea surface, recording the height of every wave that passed beneath it with the precision of an instrument that does not guess and does not round. On New Year's Day, the surrounding sea was running at roughly 12 meters from trough to crest. 12 meters is not a small wave, but it was not unusual for the North Sea in January. Experienced crews working those waters would have noted the conditions and proceeded. It was the kind of sea that is uncomfortable but not alarming, heavy but not exceptional. At 3:17 in the afternoon, the gauge recorded a single wave, rising to 25.5 meters. It was more than twice the height of every wave around it. There was no series of escalating swells to mark its approach. The record shows a sea running at 12 meters, and then a wave at 25.5 meters, and then a sea running at 12 meters again. The wave arrived, crested, and moved on. The platform held. The engineers who inspected the structure in the days that followed found damage that the conditions should not have produced. A lower deck beam had buckled under impact. Structural components showed stress signatures far beyond anything the recorded sea state could explain. The platform survived, but only within the tolerances its designers had built in for forces they could not fully predict. What the gauge had recorded was a rogue wave, almost certainly not the first to cross that sea, but the first that left a clean, instrument-verified trace in a scientific dataset. The first that could not be attributed to sensor error, observer exaggeration, or the distortion that shock and fear introduce into a person's account of what they witnessed. For centuries before that afternoon, sailors had described exactly this kind of wave. Walls of water rising from seas that should not have produced them. Holes opening in the ocean without warning. Things that arrived from conditions that did not justify them. And for centuries these reports had accumulated in maritime logs and court inquiries, and been handled with the quiet skepticism that official inquiry reserves for testimony contradicting established science. The mathematics of ocean waves, refined over 150 years, made such waves effectively impossible. Not rare, not improbable, effectively impossible. The probability was so small that dismissal seemed not just permissible but reasonable. The Draupner gauge simply measured what was there. Tonight we are going to travel into the ocean's improbable arithmetic, into the history of a wave that science declared could not exist, and the ocean kept producing, into the ships these waves took, the people who survived them, and what it means to live on the surface of a planet whose largest body of water follows rules we are still only beginning to read correctly. If you find this slow, quiet exploration of mystery something you genuinely enjoy, I'd be grateful if you'd like the video and subscribe. Letting me know in the comments where you're listening from and what time it is for you is always a quiet comfort. Now find your comfortable position. Dim the lights. Take a slow breath. We are leaving the map behind. We have become very good at predicting waves. Modern ocean forecast models calculate wave heights across the entire globe, updated every 6 hours. A cargo ship preparing to cross the North Atlantic can receive a detailed routing advisory showing the expected sea state along every mile of its intended track. The Beaufort scale, first codified in 1805 by the British naval officer Francis Beaufort, gives mariners a common language for what the sea is doing. At Beaufort Force 8, you have a gale with crested waves and streaking foam. At Force 12, you're in a hurricane. Every number on the scale corresponds to a described sea state and a range of expected wave heights. The language feels complete. The picture it paints feels stable. The professional term for the official measurement of a sea state is significant wave height. It is defined as the average height of the tallest 1/3 of waves present in an area at a given moment. When a marine forecast says the significant wave height is 12 meters, it means the top third of waves in that sea are averaging 12 meters. Around that average, the model predicts a distribution. The tallest individual waves will reach perhaps 1.5 times the significant wave height. The mathematical outliers at the very edge of the distribution will reach perhaps twice that. The model tells you, in a sea with a significant wave height of 12 meters, the largest single wave you should encounter is in the range of 20 to 24 meters. This picture felt complete because it was built on a century and a half of tested mathematics. Ocean waves are described in classical theory as the superposition of many small sinusoidal components. Each component is smooth and predictable. They add and they subtract, and the result is the irregular choppy surface we see from the deck of a ship or from the rail of a harbour wall. The mathematics is called linear wave theory. It generated useful forecasts. It allowed engineers to calculate structural loads and set safety margins. It produced a world in which the sea felt, if not tamed, at least bounded. The Beaufort scale has a top. The significant wave height has a predicted maximum. The forecasts have error bars, but those error bars narrow over time as data improves. There is something reassuring in having a vocabulary for the sea. Force 10, significant wave height 9 meters. Maximum individual wave height 18 meters. The numbers make the sea feel legible. The problem was not that the vocabulary was wrong. The problem was that it described a smaller sea than the one that exists. A professional weather routing service works by taking a ship's intended route and the available forecast data and identifying the sea states the ship will intersect along each possible track. The routing office can redirect a ship around a developing low-pressure system, recommend a speed adjustment to reach a particular stretch of ocean after the worst conditions have moved on, or propose an alternative route that avoids the severest forecast sea states entirely. Ships crossing the North Atlantic in winter use these services routinely. The mathematics governing the forecast feels, in ordinary circumstances, like a solid floor beneath the voyage. Waves begin with wind. When wind blows across open water, it drags at the surface. The water resists. That resistance builds ripples, and the ripples give the wind more surface area to push against, and the wind pushes harder, and the ripples become waves. The length of ocean the wind has been blowing over without interruption is called fetch. The longer the fetch and the longer the wind has been sustained, the more energy is transferred from air to water. and the larger the waves that result. The energy does not stay where it was created. Long-period waves, the kind generated by powerful storms and deep open ocean, travel outward from their source as swell. Swell is organized wave energy, moving efficiently through water that the storm no longer touches. It is smooth compared to the choppy conditions near the storm itself, and it can travel thousands of miles without losing much of what it carries. The water beneath a passing swell does not travel with it. Individual water particles trace circular or elliptical paths as the wave passes and return nearly to where they began. The wave is not a moving mass of water. It is a moving pattern of energy, organized into the shape of a wave. A storm in the Southern Ocean, churning in the westerly winds that circle Antarctica without obstruction, can generate swells that reach the beaches of California and Portugal, and the coasts of the Indian Ocean. The waves that arrive on a summer beach in the Northern Hemisphere often carry energy born in storms, 2 weeks and 10,000 miles away, in waters near the Antarctic convergence. The energy has been traveling all that time, losing a little to the drag of air and the friction of the deeper water, but arriving still. A rogue wave is what happens when this energy, which travels in multiple systems from multiple storms across thousands of miles, concentrates rather than disperses. It is not just a large wave. It is a convergence, and the process that produces it requires understanding something about what happens when two wave systems from different storms arrive in the same place at the same time and find in each other a kind of amplification that neither carries alone. The longest continuous fetch on Earth runs through the Southern Ocean, from roughly 40 to 60 degrees south latitude. The westerly winds blow across water uninterrupted by any significant landmass for approximately 20,000 miles. A storm that develops in this belt has an effectively unlimited runway. The energy it transfers to the sea surface has nowhere to go but into the waves, and the waves in those latitudes take it fully. A wave period describes how many seconds pass between successive crests at a fixed point. Wind chop, generated locally by nearby wind, has a period of perhaps 4 to 8 seconds. A well-developed swell, traveling from a distant storm, has a period of 12 to 20 seconds. Long-period swell moves through deep water with very little energy loss and with very little change to its shape. A swell with a period of 15 seconds, generated by a Southern Ocean storm and sent north, can cross the Pacific Ocean and still arrive as rideable surf on a beach in Hawaii days later. The energy that left Antarctic waters is still organized, still coherent, still moving. When two wave systems traveling across an ocean from different storms arrive in the same water at the same time, they interact. In most cases, the interaction is brief and unremarkable. If the crest of one wave coincides with the trough of another, they partially cancel. If the crests of two waves coincide, they briefly add, producing a wave taller than either system alone. Then the systems continue through each other and separate, and the sea returns to what it was. This is constructive interference. It is ordinary physics, and it happens continuously across the world's oceans, without producing anything remarkable. But under certain conditions, the interaction does not remain brief. The energy does not pass through and separate. Instead, it locks. The wave group becomes unstable in a way that causes energy to flow from the broader wave train into a smaller cluster of waves within it. that cluster grows, its waves steepen. The energy that was distributed across many waves concentrates into a few, or into one. The mathematical description of this process is called modulational instability. It is sometimes called the Benjamin-Fair instability, after the two researchers, T. Brooke Benjamin and J. E. Fair, who described it mathematically in 1967. The key insight from their work was that a regular wave train, one with a single wavelength, moving in a single direction, is fundamentally unstable under non-linear conditions. Small disturbances in the wave group do not dissipate, they grow. The energy reorganizes itself. The uniform wave train breaks down into groups of larger and smaller waves, and within those groups, the largest waves can reach heights that the original uniform wave train could never have produced. This is not a rare or exotic process. It occurs in wave tanks, and in numerical simulations, and in the open ocean. It is happening somewhere in the sea right now. And once it was understood, the wave that the Draupner gauge recorded on New Year's Day ceased to be impossible. It became, instead, a natural consequence of physics that the classical model had simply not been built to include. What makes the modulational instability more than a mathematical abstraction is that it has been demonstrated repeatedly in controlled conditions. In a wave tank, a paddle generates a perfectly regular wave train. One wavelength, one amplitude, and a uniform, orderly procession of crests moving at one speed. Within a few hundred wavelengths of travel, without any external forcing, the wave train develops structure. Some waves in the tank grow larger, some grow smaller. The uniform surface spontaneously becomes uneven. Energy that was evenly distributed across the wave train has concentrated into groups. The groups persist. The largest waves in the groups continue to grow at the expense of the smaller waves around them. This behavior was known to wave physicists through the 1960s. Benjamin and Fair published their mathematical analysis in the Journal of Fluid Mechanics in 1967. The paper was read in the relevant research communities. It was cited. It influenced understanding of wave dynamics in physics and fluid mechanics departments. But the institution that sets ship design standards and the institution that studies fundamental wave physics are not the same institution. They did not share a common language for the findings to travel through efficiently. Not every stretch of ocean produces rogue waves with equal frequency, and the eastern coast of South Africa has, for centuries, had a reputation for extremes. The reason is the Agulhas Current. It flows southward along that coastline, moving warm water from the Indian Ocean toward the tip of the continent. Its speed can reach 2.5 meters per second. It is a powerful and consistent southward flowing current, occupying a strip of ocean several dozen miles wide and pressed against the continental shelf by the Earth's rotation and the shape of the coastline. From the southwest, the Southern Ocean sends its swell. The storms that circle Antarctica without obstruction generate some of the world's largest and most energetic swells, and those swells move northeast. They travel from waters near Antarctica toward the Indian Ocean and toward the South Atlantic, and on the eastern coast of South Africa, they meet the Agulhas Current, traveling in exactly the opposite direction. When a swell traveling in one direction encounters a strong current flowing against it, the wave's wavelength compresses. The same energy is packed into a shorter distance. The waves slow down relative to the seafloor and to the current. They become steeper. The ratio of height to wavelength increases. A wave that was long and smooth and deep ocean elegant becomes something shorter, stepper, and more dangerous. The seafloor topography along this coast, rising toward the continental shelf, compounds this effect. The interaction between opposing current, opposing swell, and changing depth creates conditions that the mathematical models of the 20th century did not fully account for. Sailors have been filing reports of unusual and extreme waves off the eastern coast of South Africa for as long as records have been kept. For most of that time, those reports were treated as descriptions of rough seas, as normal storm conditions that perhaps frightened inexperienced observers more than the conditions warranted. The pattern that was visible in those reports was not assembled into evidence until the science of rogue waves made it possible to understand what the current was doing to the swell. The Portuguese navigators, who first rounded the Cape of Good Hope in the late 1400s, were the first Europeans to leave systematic records of what the sea does along that coast. Bartolomeo Dias lost ships to southern African waters in 1488. Vasco da Gama's voyage of 1498 produced accounts of sea conditions that did not match anything in the Mediterranean or Atlantic. Experience the navigators carried with them. The Cape itself was called, in one tradition, the Cape of Storms. The Portuguese crown later renamed it the Cape of Good Hope, the name better suited for the purposes of commerce and recruitment. What those early navigators were encountering, without the scientific framework to understand it, was the interaction between the Agulhas Current and the Southern Ocean swell. The current is warm, fast, and consistent. The swell arriving from the Antarctic storms is powerful and long period. When they meet in opposition, the physics does not average them. It amplifies the extremes. A moderate swell in open ocean becomes steep and unpredictable in the Agulhas zone in ways that a forecast based only on the generating storm would not predict. The ship enters conditions that the weather advises should be manageable. The sea produces conditions that are not. The historical record on rogue waves is extensive and consistent. It was simply never treated as a record. From the 1600s onward, as European maritime trade expanded and ship logs became standardized documents, accounts of extraordinary waves began to accumulate. Captains of competent ships in the documented sea states described waves that rose without warning to heights their instruments could not measure, and their experience could not account for. The logs were filed. The inquiries took testimony. The conclusions almost invariably attributed the ship's difficulties to storm conditions, to navigational error, or to the imprecision of human observation under stress. There was a structural reason this pattern continued for 300 years. Each inquiry examined one incident. No mechanism existed to compare the incident being examined with the 100 others that had preceded it. A captain in 1840 describing a wave of extraordinary height off the South African coast was not read alongside a captain from 1790 describing an identical experience in the same waters. The aggregate was invisible because no one was constructing it. In 1861, the Royal Charter was lost off the coast of Wales. She was a British clipper ship. The conditions that witnesses on shore and nearby vessels described included a single wave of exceptional size, that struck the ship and did not let go. The official inquiry concluded that the loss was due to the severity of the storm. It almost certainly was, but the inquiry did not examine whether a single wave of the height described could have been produced by the storm conditions recorded. The assumption was that if the storm was bad enough, the wave was explicable. The height was not examined. A captain who returned from a voyage and described a wave that rose 30 or 40 feet above the masts of a large ship was, in the culture of 19th century maritime inquiry, describing something that called his judgment into question. The mathematics said it was impossible. The mathematics was trusted over the witness. One case from the early years of the 19th century is instructive precisely because it was handled in the way such cases were always handled. A British merchant vessel returning from the East Indies filed a report in 1814 describing an encounter east of the Cape of Good Hope in which the ship was struck by a single wave, the captain estimated at 30 to 40 meters. The ship survived, badly damaged. The captain, whose competence was not in question, stated in the official log that the wave rose without warning from a sea that was rough, but not exceptional by the standards of that route. The inquiry board heard the report. The official record notes that conditions were severe on the route at the time, and that the damage was consistent with extreme storm conditions. The captain's estimate of wave height was noted and set aside. There was no scientific framework within which such a height could be evaluated. Since the mathematics did not permit it, the reported height must be an overestimate, or the captain must have experienced some distortion in the moment. The ship's damage was real. The wave's characteristics were not examined. A rogue wave does not have a single shape. Depending on the conditions that produce it and the sea state it arrives in, it can take 3 distinct forms, and each form is dangerous in a different way. The first is the wall of water. It arrives as a nearly vertical face, steep enough that the ship cannot ride up and over it in the normal way a wave is ridden. The face is not a slope, it is a wall. The wave often announces itself with a deepening trough that appears first, a sudden emptying of the sea ahead of the ship. The bow noses down into this trough, and the ship is angled downward when the wave arrives. The impact is not the rolling motion of a large but rideable wave. It is a collision. The second form is sometimes called the hole in the sea. A circular or oval depression opens in the surface, a collapse in the sea's geometry that a ship can fall into before any vertical wall arrives. Ships have described their bows dropping away into a void with no warning before a wall of white water filled the hole from all sides. The effect is less a wave arriving than the sea briefly opening and then closing. The third form is the Three Sisters, 3 large waves arriving in rapid succession, each separated by a short trough. A ship struck by the first is still recovering when the second arrives. It is taking on water and losing way. The third finds a vessel already compromised. The Three Sisters are considered among the most dangerous configurations, because no single wave in the sequence need be catastrophic. It is the sequence that destroys. What all 3 forms share is a quality of wrongness. The wave does not fit the sea it arrives in. It is too large, too steep, too sudden. Sailors who have survived encounters consistently describe this. Not just the size, but the sense that the sea has done something it should not have done. Something arrived that the conditions did not announce, and the training did not prepare for. The wall of water form is the most often described and the most dramatic to imagine from the outside. What survivors who have encountered it from a ship's bridge describe is a face that extends above the horizon line, which requires the wave to be very tall for a crest to be visible above the horizon from a bridge 20 meters up. The wave must be clearing that height by a significant margin. The face is not a slope that a ship might climb. It is steep enough that the hydrodynamic relationship between ship and wave breaks down entirely. A ship approaching a rideable swell rises with the swell. A ship approaching a wall does not rise, it collides. The hole in the sea is in some ways the more insidious form, because it provides no visible announcement at the surface. A wall of water can, at least, be seen approaching. The hole appears when the sea surface collapses beneath the ship. The bow drops into the depression at an angle that points the ship downward just as the water returns. A ship in a hole is, for a few seconds, diving rather than floating. The wave that arrives to fill the hole finds the ship already in the worst possible orientation to receive it. In December of 1978, the MV München set out from the port of Hamburg, bound for Savannah, Georgia. The München was a container ship registered in Germany and operated by the Hamburg America Line. She was 261 meters long, built 3 years earlier to the most current engineering standards, and rated among the most capable vessels in the North Atlantic trade. Her crew numbered 28 experienced officers and sailors who had made this crossing many times. The North Atlantic in December is reliably difficult. The winds from Iceland to the Azores bring deep winter lows that stack waves against the eastward running Gulf Stream and the southward running current from the Labrador Sea. The München was built for exactly these conditions. Her designers had specified her to survive any sea state the route could reasonably produce. Her last confirmed contact was a routine radio call in the early hours of December 12th. The weather was rough but not exceptional. Nothing in the traffic suggested emergency. The München was on track, on schedule, and performing normally. She was never heard from again. The distress signals that were eventually picked up were fragmentary. An automated distress beacon began transmitting, but the signal contained only the most basic identification information. There was no extended voice contact, no distress call in the usual form, no description of conditions. The signal simply indicated that the München was in distress and gave her last known position. The search covered an enormous area of the North Atlantic. What searchers found was scattered debris and very little of it. A lifeboat, a life ring, some cargo containers. For a ship of the München's size, the volume of recoverable material was almost nothing. A ship as large as she was does not simply vanish into a moderate winter North Atlantic. Something had happened very quickly, and the debris field, what little there was, suggested the ship had come apart, under forces applied from an unexpected direction. The North Atlantic, in December, has a specific character that experienced crews know before they see it. The Icelandic low, the persistent pattern of low-pressure systems that forms over the cold northern waters in winter, generates one of the world's most reliable sequences of storms. Every few days a new system develops and moves south and east across the ocean, deepening as it goes. The wave trains from successive systems do not always have time to separate cleanly before the next storm begins to add its own energy to the sea. The result is a sea state composed of overlapping contributions from the current storm and from the 2 or 3 that preceded it. Different wavelengths, different periods, different directions. The München's officers would have known this environment well. The route from Hamburg to Savannah was a route they had made before. The ship was built for North Atlantic service, and North Atlantic service in December meant exactly this kind of layered and complex sea. Nothing in the ship's history or the crew's record suggested any reason for special concern on this particular crossing. The inquiry into the loss of the München was thorough and, in the end, honest about what it could not explain. The evidence assembled from the debris was small in volume, but precise in what it implied. Investigators recovered the emergency position indicating radio beacon from the starboard bridge wing of the München. These beacons are mounted in a bracket with a retaining pin designed to hold the device in place under any sea condition the bridge wing might reasonably experience. The pin that had held the München's beacon was bent. The bending was inward. The force that had deformed the pin had come from outside and above, pressing in toward the ship's centerline rather than outward from it. The bridge wing on a ship of the München's class is mounted roughly 20 meters above the waterline. 20 meters is 6 stories. The retaining pin had been bent by a force coming down from above the bridge wing level onto a device mounted 6 stories up. Investigators also examined a steel door on the bridge deck of a second ship that had been in similar waters during the same period and had survived an extreme encounter. That door, also mounted well above the normal maximum reach of waves in the recorded sea state, had been bent inward. The deformation was consistent with a wave striking it from outside at an angle that should have been impossible for any wave generated by the conditions recorded. The inquiry concluded that the München had been struck by a wave of extraordinary height, approaching from a direction that allowed it to impact the upper structure of the ship. A wave that could reach the bridge wing at 20 meters. Given the München's beam and freeboard, the wave height implied was somewhere north of 25 meters. The ship had gone down quickly. The distress signal had barely begun before contact was lost. The sea had returned to its recorded state. There was nothing left to examine except the bent pin and the absence. The bent pin became something close to a technical landmark in the investigation of rogue waves, not because it was conclusive on its own, but because of what it required an inquiry to explain. For a device mounted 20 meters above the waterline to be struck and partially deformed by a force coming from above and outside, the inquiry needed to identify the source of that force. The engineering review was clear. The München had no structure above the bridge wing position at that deck level that could have collapsed onto the lifebuoy bracket. The source of the force was external. Something had struck the bracket from outside and above at a height of 20 meters. In the sea state recorded for the area at the time of the loss, the significant wave height was estimated from the nearest weather observations at roughly 12 meters. The maximum wave predicted by the Rayleigh distribution for that sea state was perhaps 20 to 22 meters at the extreme outer edge of the probability tail. 25 meters was not within the prediction. But the inquiry was not working from the probability distribution. It was working from the physical evidence in hand. The München was not alone. Insurance records maintained by Lloyd's of London and other maritime underwriters have, for decades, shown a pattern in the loss of large commercial vessels that statistical analysis never quite accounted for. Ships lost in deep water, ships lost in sea states that their design specifications should have allowed them to survive, ships that gave no distress signal or gave one too brief to be useful, ships that disappeared so quickly that their position at time of loss could only be estimated from their last reported position and their known speed. Ships from which almost nothing was recovered. The pace of these losses through the 1970s, 80s, and 90s averaged something close to 2 large cargo vessels lost per week across the global fleet. Not all of these were rogue wave events. Some were fire, collision, structural failure from other causes, or human error. But investigators attempting to identify the mechanism of loss for vessels that sank quickly in deep water, in conditions that should not have been fatal, found that rogue wave impact was increasingly the most plausible explanation. NOAA estimates suggest that in the 2 decades before the Draupner measurement forced a scientific reassessment of rogue wave probability. More than 200 large ships were lost in circumstances consistent with catastrophic wave impact. These are not ships that sank in hurricanes or ran onto reefs. These are ships that were found missing after routine voyages, their last known positions in deep ocean, their loss records carrying the notation that conditions were poor but not exceptional. The ocean does not issue receipts. A ship that sinks quickly in 3,000 meters of water leaves almost nothing for an inquiry to examine. The investigators have the debris, the last position, the weather record, and a calculation about what a ship of that class should have survived. When the calculation fails to explain the loss, the official record says, cause unknown. The sea knows. One ship illustrates the pattern with particular clarity. The MV Derbyshire was a British bulk carrier and the largest British merchant vessel of her era, lost in September of 1980, with all 44 crew during Typhoon Orchid southeast of Japan. No distress signal was received. No survivors were found. The initial inquiry attributed the loss to the typhoon and closed. For 15 years, the Derbyshire lay at the bottom of the Pacific. Then a series of investigations, culminating in an underwater survey of the wreck site in the 1990s, found the ship largely intact on the seafloor with damage concentrated in the bow sections. Computer modeling of the wreck was used to reconstruct the sequence of structural failures. The findings suggested that the bow had been struck by a large wave that forced the forward hatches open, allowing rapid flooding of the forward compartments and driving the bow down into the sea. On March 2nd of 2001, the passenger expedition ship Caledonian Star was in the Drake Passage. This is the body of water that separates the tip of South America from the Antarctic Peninsula. The Drake Passage is roughly 600 miles wide at its narrowest point. All of the energy that the Southern Ocean's westerly winds generate as they circle Antarctica without interruption is compressed through this channel. The waves that move through it are among the largest in the open ocean. Mariners have known this for centuries. The Drake Passage earned its name and its reputation long before rogue wave science existed. The Caledonian Star was a well-maintained vessel operating a tourist expedition to Antarctica. Her bridge was positioned 32 meters above the waterline. 32 meters is over 10 stories. In any sea state that the Drake Passage routinely produces, in any wave that linear wave theory predicted as the maximum possible for the conditions, the bridge would be entirely beyond the reach of water. In the early morning hours, the crew reported seeing a wave approaching from ahead that was clearly not the same as the waves around it. The sea had been rough. This was something else. The wave was later estimated at 30 meters. It struck the ship. The bridge windows, made of reinforced glass and set 10 stories above the sea surface, shattered. Water flooded onto the bridge. 2 crew members were injured. The ship lost electrical power briefly as water reached systems that should never have been touched. The navigation room took damage. The vessel survived. The bridge was at 32 meters. The wave was estimated at 30. The gap between those numbers is 2 meters, 6 feet. This is the margin by which the Caledonian Star retained steerage, rather than losing it entirely. The official report noted the incident with clinical precision. The windows at 32 meters above the waterline had been broken by water. The Drake Passage that night was running what experienced hands would call a typical crossing. Significant wave height between 8 and 10 meters, wind in the mid-30s of knots, swell from the west, with some cross swell from the northwest. These are conditions that a professional crew approaching Antarctica regards as demanding but normal. They are the conditions for which the Caledonian Star was designed and crewed. The officer on the bridge first observed the anomalous wave when it was approximately half a mile away. At the ship's speed and the wave's estimated speed, this gave perhaps 30 seconds of warning. 30 seconds is not enough time to significantly alter a large ship's heading or speed. The officer called a warning to the crew and held on. The wave struck the bow first, and the ship's bow rose on the wave's face. Then the crest passed the bow, and the ship was in the trough behind the breaking crest. The force that took out the bridge windows was not the wave arriving at bridge level. It was the water coming over the crest of the wave and falling. At 32 meters above the waterline, the bridge had been reached not by a wave climbing to that height, but by a wave's crown collapsing downward onto it. The wave height was estimated at 30 meters. The water reached 32. 2 meters. 2 meters was the difference between a damaged bridge and a flooded one, between crew who could recover control and crew who could not. 6 years before the Caledonian Star's encounter, on September 11th of 1995, Captain Ronald Warwick was on the bridge of the Queen Elizabeth II when the lookouts called his attention to what was approaching from ahead. The Queen Elizabeth II was in the North Atlantic, in seas made severe by Hurricane Louise, one of the larger Atlantic hurricanes of that year. The ship was large, modern, and built to handle rough North Atlantic crossings. She had been in worse conditions. The hurricane had been tracked, and the routing had accounted for what the models predicted. What Captain Warwick described afterward was a wave he estimated at 29 meters, 95 feet. He said it resembled the White Cliffs of Dover seen from the water, which is the comparison a person reaches for when they have run out of nautical language, for something that does not fit the vocabulary of the sea. The cliffs at Dover reach in places to over 100 meters, But their base at the water is what Warwick was describing. A white wall rising almost vertically from a sea that had just dropped away in the trough ahead of it. The ship rose on the wave's face. Her bow climbed at an angle steep enough that Warwick could see through the bridge windows nothing but white water and sky. The stern came partly clear of the sea. The ship crested and fell into the trough on the other side. The descent was, by multiple accounts, violent. Below decks, the impact threw passengers and crew. One passenger suffered a broken leg. Structural damage was found in the forward sections. The ship survived. The wave was not predicted by the models that governed the ship's routing. It arrived from a direction, and at a height that the models, processing the hurricane's data, had not produced. The sea, running at a significant wave height of roughly 12 meters, had generated a wave more than twice that height. The Rayleigh distribution said this should be essentially impossible. The ship's bow camera had it on video. What Captain Warwick's account adds beyond the bare facts is a texture that official inquiry language rarely captures. He had crossed the Atlantic many times and been in severe weather before. He described the wave as belonging to a different category from everything he had previously encountered. Not different in degree, but in kind. The sea around the ship that afternoon was already severe. Hurricane Luis was generating dangerous conditions, and the ship was moving through them. The waves were large, and then something arrived that was not large in the same way the surrounding waves were large. The word that appears in Warwick's account, and in the accounts of other rogue wave survivors, is wrong. Not large, not extreme, wrong. The wave does not look the way waves in those conditions are supposed to look. Its steepness does not match the surrounding sea state. Its height does not follow from the wave that preceded it. Experienced mariners, people whose professional lives are organized around reading the sea, describe rogue waves not primarily as large, but as inconsistent, out of place, as if a wave from a different ocean had arrived in this one. What survivors describe does not sound like a weather event. The people who have encountered rogue waves and return to say what the experience was like share certain details across all their accounts, regardless of when the encounter occurred, what vessel they were on, or what sea state preceded it. These details do not vary, the way witnesses' accounts of storms vary. They are consistent in a way that suggests they are describing the same specific physical phenomenon rather than simply different degrees of severity. The first consistent detail is the trough. Before the wave itself, many survivors describe a sudden and alarming absence of water ahead of them. The sea drops away. The ship noses down into the depression. For a few seconds, the vessel is angled toward a sea surface that is lower than it should be, and the wave has not arrived yet. The trough is the first announcement. The second consistent detail is the color. The wave, when it hits, is not blue. It is white. Not the white of spray or foam, but a dense, solid, opaque white that survivors describe as resembling a wall of concrete more than water. It does not have the translucency that wave water has when you look through a breaking crest from the side. It arrives as solid matter. The third consistent detail is the sound. Some survivors report a roar that arrives before the wave is visible, a deep resonance that the body feels before the ears identify it. Others describe near silence in the moments before impact, a drop in the ambient noise of the storm that in hindsight reads as the sea gathering itself. What survivors do not describe is a gradual increase in wave height. They do not describe riding up through a series of escalating swells toward a final large one. They describe an interruption, a discontinuity, the sea doing something that did not follow from what it had been doing. That quality of discontinuity is perhaps the most important thing the accounts preserve, and it is the quality that classical wave theory had no framework for producing. The brevity of the encounter is what survivors consistently struggle to reconcile with the intensity of the memory it produces. The total elapsed time from the moment a rogue wave becomes visible to the moment it has passed is, for most ships and most encounters, measured in seconds. 15, 20, 30 in cases where speed and heading allow slightly more warning. In those seconds, the watch on the bridge moves from normal routine through impact to the immediate aftermath. From the routine of a night crossing to something that does not fit any prior frame of reference. The immediate aftermath is described by survivors with a specific quality of detail that stress psychology might recognize. The mind in extreme situations often records very precisely while not processing normally. Crew members who survived the Caledonian Star's encounter have described remembering the first seconds after impact with unusual sharpness. Water moving off equipment, glass on the floor, the specific sound the radar made as it failed, the angle of the ship's lean, and the color of the water still on the bridge. Ordinary experience does not typically lay down memory with this resolution. Extreme experience sometimes does. In 2000, the European Space Agency funded a research project called MaxWave. Its purpose was to use satellite radar data to look directly at the ocean's surface at global scale and count waves that exceeded accepted maximum heights. The satellites involved carried synthetic aperture radar, an imaging system that works by bouncing radar pulses off the sea surface and measuring what comes back. Rough water scatters radar differently than smooth water. Large waves produce distinctive signatures. The system could detect surface features, including the height of individual waves, from an orbit hundreds of miles above the Earth. The coverage was not continuous, but was sufficient to sample large areas of the global ocean across each satellite pass. Over 3 weeks in 2001, the MaxWave project collected data and analyzed it. The question the researchers asked was straightforward. How many waves exceeding 25 meters in height could be identified across the global ocean in this period? 25 meters was chosen because it was roughly twice the significant wave height of a severe North Atlantic sea state, well beyond the maximum predicted by the Rayleigh distribution for any plausible sea state. The answer was more than 10. In 3 weeks across the global ocean, the satellites identified more than 10 individual waves that cleared 25 meters, 10 in 21 days. The classical models using the Rayleigh distribution derived from linear wave theory predicted that a wave of this height should appear at any fixed location in the ocean approximately once every 10,000 years. Even accounting for the global scale, the mathematics did not produce 10 in 3 weeks. The satellites had found them appearing at a rate roughly 4 or 5 orders of magnitude more frequent than the equations predicted. The MaxWave results were presented at a European Space Agency workshop in 2003 and were considered within the wave science community as settling. The debate about whether rogue waves were real and frequent had been conducted long enough. They were. The European remote sensing satellites that gathered the maxwave data were not built for wave research. They carried synthetic aperture radar, primarily for mapping land surfaces and ice coverage. But the instrument's sensitivity to surface texture made it useful for ocean surface work as well. Synthetic aperture radar works by processing the returns from many individual pulses to simulate the resolution of a much larger antenna. The result is an image of the surface with spatial resolution fine enough to detect wave features across large swathes of ocean in a single pass. The MaxWave team developed algorithms for identifying individual large wave signatures in the radar data, distinguishing genuine rogue events from other sea surface features that might produce ambiguous returns. The methodology was validated against buoy data from locations where both satellite and surface measurements were available simultaneously. The agreement was sufficient to establish that what the satellite was counting as a large wave was, in fact, a large wave. The equation that failed was not a bad equation. It was the right equation for the physics it was designed to describe. Linear wave theory treats ocean waves as the sum of many independent sinusoidal components. Each component has a fixed wavelength, a fixed amplitude, and a fixed direction of travel. They do not influence each other in any fundamental way. They add when they coincide and subtract when they oppose. And the result is the complex, irregular sea surface we observe. This framework, which physicists call superposition, is accurate and powerful within its assumptions. From this framework, wave scientists derive the probability distribution of wave heights in a given sea state. The distribution they arrived at is called the Rayleigh distribution. It is a well-behaved distribution with a tail that falls off exponentially. As wave height increases beyond the significant wave height, the probability of encountering a wave that tall drops steeply. At twice the significant wave height, the drop has become so steep that the probability is negligible in practical terms. The distribution says that such a wave should appear at any fixed point in the ocean roughly once every 10,000 years. The assumption the Rayleigh distribution rests on is that the wave components are statistically independent and that the wave system is linear. These assumptions are good approximations for most sea states most of the time. The mathematics they produce is useful for most engineering purposes most of the time. The problem is that ocean waves are not linear. Under certain conditions, the wave components interact non-linearly. Energy flows between them. Wave groups become self-reinforcing rather than dispersive. The modulational instability that Benjamin and Fair described in 1967 produces wave height distributions with heavier tails than the Rayleigh distribution predicts. Much heavier, not slightly heavier. The extreme events at the tail of the distribution are far more probable in a non-linear sea than linear theory would allow. The gap between the two distributions is where the rogue waves live, and for a century the models used to design ships and set safety standards had been built on the linear side of that gap. The institutional distance between wave physics research and maritime engineering standards is one of the less examined factors in how the linear model stayed in place for so long after its limits were known. The Benjamin Fair paper appeared in 1967. The MaxWave Results were presented in 2003. 36 years passed between the mathematical demonstration that linear wave theory could not account for the observed tail of the wave height distribution and the observational confirmation that the tail was far heavier than the linear model predicted. In those 36 years, classification societies continued to certify ships to design standards derived from the linear model. Weather routing services continued to provide forecasts that did not account for modulational instability. The Draupner wave in 1995 prompted internal discussions in the wave science community, but remained a single data point. In complex physical systems, a single data point does not typically overturn decades of established practice, even a striking one. The system requires accumulation. The dark mirror of the rogue wave story is not the waves themselves, it is the ships. For most of the 20th century, the standard design wave used by classification societies when certifying the structural integrity of open ocean cargo ships was 15 meters. A ship whose frame and hull plating could survive a 15-meter wave was considered fit for global ocean routes, including the North Atlantic, the South African coast, and the Drake Passage. 15 meters is 50 feet. It is a serious wave by any ordinary measure. It is not the wave the Draupner gauge measured. It is not the wave that struck the München's bridge. It is not what Captain Warwick saw approaching the Queen Elizabeth II. The classification societies are the bodies, Lloyd's Register among them, that set the technical standards ships must meet to be insured and to operate. Their standards carry the force of market law. A ship that cannot be insured can't trade. For decades, their design wave standard was calibrated to what the linear models predicted as the practical maximum in a severe sea state. The linear models said 15 meters was a safe upper bound. After the Draupner wave, and after the max wave results, and after the formal reclassification of rogue waves from legend to documented phenomenon, the standards began to move. They have moved. The current guidelines are more generous, but they moved slowly, shaped by the cost of rebuilding a global fleet to a new specification, by the institutional weight of standards bodies that had certified the same figures for generations, and by the difficulty of agreeing on what the new figures should be when the non-linear models do not produce a clean single maximum the way the Rayleigh distribution did. Container ships and bulk carriers cross rogue wave zones today that were identified in the max wave data. They cross the Agulhas zone and the Drake Passage and the winter North Atlantic, carrying more cargo on tighter schedules with thinner margins than the ships that preceded them. The waves are still there. The mathematics governing ship design has improved. The margin between them is a policy question dressed as an engineering question, and the ocean does not participate in the policy discussion. The economic dimension of the gap between what the science showed and what the standards required is not difficult to calculate and has not been invisible. Revising the design wave standard upward by 10 or 15 meters would require the structural reinforcement of essentially every large cargo vessel in the global commercial fleet. For a fleet of tens of thousands of ships, at a cost of millions of dollars per vessel, the aggregate is a figure that the industry cannot absorb without a corresponding rise in freight rates, that the global economy that depends on that freight would also feel. The classification societies that set design standards operate at the intersection of engineering and commercial reality. Their standard-setting process involves not only the physics of what waves do to ships, but a negotiation over what ships can practically be required to survive, given the economic constraints of the industry they certify. The outcome of that negotiation has historically been a standard calibrated toward what the linear models predicted as extreme, rather than what the non-linear reality produced. Rogue waves are not evenly distributed across the ocean's surface. They concentrate in places where the conditions for their formation converge, and those places have been known, in practical terms, to mariners long before the science existed to explain them. The Agulhas Current zone of South Africa's eastern coast is among the most reliably active. The current opposing Southern Ocean swell, the compression of wavelength and the steepening of crests, the shallow seafloor shelf amplifying the interaction. All of these converge along a stretch of coastline that has been producing rogue wave reports since the first European ships rounded the Cape. Sailors called the waters off Port Elizabeth and East London difficult in a way that the surrounding weather alone did not entirely explain. The North Sea generates rogue waves through a different mechanism. Weather systems from the Atlantic and from the Norwegian Sea and from the Baltic produce wave trains from multiple directions simultaneously. The North Sea is relatively shallow, which means the seafloor interacts with the waves passing over it. The crossing of swell systems from different directions in shallow water with complex bathymetry creates conditions for constructive interference and modulational growth that do not exist in the same form in deep open ocean. The Draupner platform was in the North Sea. The Drake Passage compresses the Southern Ocean's energy into a channel and accelerates it. The waves that emerge from the Drake into the South Atlantic carry more energy per unit of width than ocean waves almost anywhere else on Earth. The Northwestern Pacific in winter, where storm tracks from Siberia and from the Central Pacific cross each other's swell systems, produces its own complex multi-directional sea state. The record of ship losses in that region, examined now with rogue wave probability in mind, tells a familiar story. These are the places where the ocean is most concentrated in its improbability. They are also, all of them, major shipping routes. The sea does not organize its extremes around our navigation charts. The Gulf Stream zone off the eastern coast of North America shares certain characteristics with the Agulhas zone that make it worth understanding alongside it. The stream flows northeast, along the continental shelf before turning east into the open North Atlantic. Winter storms moving northeast across the continent generate wave trains that can travel out to sea and encounter the northeast flowing current in a configuration similar to, if less intense than, the one that characterizes the Agulhas zone. The current is somewhat slower and less sharply defined than the Agulhas, and the Southern Ocean swell does not reach this region with the same power it brings to South Africa's eastern coast. But the mechanism is present. Opposing current and opposing swell, in water shallow enough to matter, produce conditions that favor wave growth beyond what the generating storm alone would predict. Monitoring of the hotspot zones has improved substantially since the MaxWave study. Dedicated wave buoy arrays have been deployed in the Agulhas zone and in the Drake Passage. Satellite radar coverage of the global ocean has become more systematic. The data being collected now is beginning to build, at global scale and over time, the picture that centuries of sailors' reports were attempting to describe from individual ships in individual moments without the tools to be believed. Somewhere in the ocean right now, the conditions for a rogue wave are assembling. 2 or 3 swell systems are converging. A current is pressing against them, compressing wavelengths, pushing crests towards steeper angles. The modulational instability is beginning to do what the mathematics requires it to do: concentrate energy rather than disperse it. A group of waves within the broader sea is growing at the expense of the waves around it. In perhaps 20 minutes, in perhaps 2 hours, a wave will form that is twice the height of everything near it. It will persist for 30 seconds or 90 seconds. It will move through the sea at 20 or 30 knots, and then the energy will disperse, and the sea will close over where it was, and nothing will remain to mark that it passed. Most rogue waves cross empty water. The ocean is mostly empty of vessels, relative to its scale. Most rogue waves form, persist, and dissolve in water that no instrument has been placed to measure, on a stretch of sea that no ship is crossing at that moment. They exist, reach their maximum height, and are gone. And the only record is what the mathematics implies about how often they should occur. The ones we know about are the ones that happen to encounter something. The Draupner platform, the München, the Caledonian Star, the Queen Elizabeth II. The fraction of rogue waves that left a record is a fraction of something far larger. The ocean produces them at a rate the max wave satellites begin to suggest, more than 10 in 3 weeks, globally, at heights exceeding 25 meters alone. Below 25 meters, the count is far higher. Below 20 meters, higher still. The sea is generating extremes at a pace that the linear models never predicted, and it has been generating them at this pace for as long as the sea has been the sea. We live on the surface of a planet covered to 7/10 of its area by water, and we have been crossing that water in ships for perhaps 6,000 years, and we have been building formal mathematical descriptions of how it behaves for about 150 years, and those descriptions were wrong in a specific way, about a specific kind of extreme event. The wrongness was not trivial. It governed ship design, it shaped safety standards, it determined how the testimony of witnesses was treated in official inquiries, and the sea kept producing rogue waves at whatever rate the physics required, without reference to the equations. There is something that does not feel like failure in this. If you stay with it, the sea that does not fit the model is more interesting than the sea that does. The wave that should not exist is evidence that the ocean is larger than the box we built for it. We have better models now. They are still not the sea. They are descriptions of the sea, written in a language the sea does not speak. The rogue wave is still out there, forming somewhere in the dark water. It will leave no record. The sea will give nothing of it away. And somewhere in that darkness, which is most of the ocean most of the time, the mathematics continues, patient, indifferent, and more strange than the equations we have written for it. That is not a warning. It is simply what the ocean is. And there is something quietly enormous in the reminder that the world's largest body of water still follows rules larger and stranger than any we have yet written down.